Okay. So firstly, we are currently doing second chapter. Okay, Fia. And let me revise whatever we have done so far. So electric potential we are doing. The first thing that we did was the work done in bringing a charge from, let's say, initial point to final. So this was, and this was in the presence of electric. Okay, so in the presence of electric field, we are moving a charge from initial point to final point, and this is minus q initial to final and dot. Yeah. So this was the work, and then we found out that this electric field would be of two types. Okay, so this can be uniform, just like this one. Let's say I plus 4j plus 5. So this is one kind of electric field. Now there is another kind of electric field which would be very, right, non-uniform. So in this case, the electric field will vary when we change the position, or yeah, whenever we change the position. So let's say this would be something like 3xi plus 4xy square j, and let's say z. So these can be this is the example of variable electric. So for the case of uniform electric field, the work done is simply minus q e dot r final minus r, right? And whenever I say something wrong, Aisha, you please correct. Okay. So this is the work done due to the uniform, and
Sir, in
then
the variable, it is 3x I cap, 4x y square j cap plus, what is that?
ZQK cap. So I just took some variable right. So you can see that this is dependent upon x, y, and z. So whenever I change position of x, y, z, my electric field will change. Right. So let's say if I am at 1, comma 3, comma 4, so my electric field would be different. If I am at 3, comma 5, comma 6, so my electric field would be different. But for this case, no matter what is my position, my electric field would be the same. Right.
Yes,
Okay.
sir.
Okay. So for uniform electric field, this is my work done, and I'm quickly revising whatever we have done so far. Right. So, and then for the variable case, this is the same as that we talked about. Right. So initial.
Sir, can you scroll up little bit?
Yeah. Are you noting it down? Then it will take time.
Yes, sir. Done.
Okay. And then we have. So you are taking the CBSE classes, right? So who is taking your CBSE classes? Was it?
Amna ma'am is taking, sir.
Okay. Yeah. So then we have this variable kind of electric. Right? For variable electric field, this is my work. And what is the need of this work? Right. So this decides what is the. So the next topic that I did after that is the electric potential and potential difference. Potential difference. Okay. So this work done is related to this electric potential and potential. So let's say that this potential is defined as work done bringing a charge from infinity to a point. So work done in bringing a unit charge from infinity to point P is called the electric potential, right? So if I write W from infinity to point P, this would be how much? Minus of Q and E dot dr, and this is from infinity to point, right? And then this Q is there, so this gets cancelled, and we have electric potential, which is minus infinity to point P E dot dr. So this is my electric potential, right? So this can again would be of two form. This can be uniform or this can be basic. But let's say that I am taking a charge from, let's say, some initial point to some final point. Then what happens? So then we already know that the uh, the potential, right? So the work done in bringing a charge from initial point to final point, it is related with this potential, and this is V final minus potential, right? So this is the work done from bringing a charge from one fixed point to another fixed point. Okay, and we also know that what is the work done in bringing a charge from initial to final point. So this is equal to minus Q and E dot T from initial to final, right? So this Q cancel and we get P final minus P initial, which is minus E dot dr from initial to final. So this is called the potential. Earlier, when we were bringing a charge from infinity to a fixed point, so that was potential difference, right? And that was electric potential, and this is potential difference, right? So when I bring a charge from infinity to point P, that is electric potential, and when I bring a charge from a fixed point to another fixed point, so that is called the potential. Okay. So again, in here, this electric field could be of two types. This can be uniform, and this again can be basic, right? So for uniform case, my potential difference, which is V final minus V initial, this is simply minus E dot R final minus R initial, right? So I'm not doing any equation because we have done so many questions based on this. So yeah, this is due to the uniform electric field,
But
right?
yeah, how to study, sir? I don't know. Like, I'm attending the first class, so how the
Yeah,
questions are will be asked? Nothing. I have
yeah,
idea.
yeah. So what I will do is that I will send you this one note, right? Credential, not the credential. I will send you this one note, PDF of this one. Okay, and then you go through all the questions. Okay.
Sir, only this concept is done.
Yeah, no, we have calculated the electric potential due to numerous configuration, numerous distributions. So I will talk about that also. Right. In today's class, I will be talking about electric field conversion and gradient of potential. So electric field can be written as gradient of potential. So I will in today's class I will talk about that, but I will just giving a quick recap whatever we have done in the second chapter. Okay. Now for the case of variable electric field, the potential difference is simply minus initial to final point E dot T, and some form of electric field would be given. So this is the potential, right? Now, the next topic that I did was we calculated the electric potential due to different kinds of distribution. Electric potential due to different distributions. First one was the simpler case. So first we calculated the electric potential of point charge. So how much is this? Pia, do you remember?
No, sir.
Okay, so this is simply KQ by R, right? So due to a
Yes, sir.
due to a source charge Q, and we calculate the potential at this distance, so this is simply KQ by R, right? Okay, and then we calculated the electric potential due to multiple charges. Okay, and we found out that the total electric potential is algebraic sum of the individual, right? So let's say if we have n charges, so potential would be just sum of all the individual charges, right? So let's say you did the example of this kind of question, right? So this was, let's say, Q minus Q minus, or let's say this is 2Q minus 2. So this, and then you calculated the electric potential at your. So now you have four charges. So V would be simply V1 plus V2 plus V2 plus. So this kind of distribution. And then after this, what did we do, Aisha? Yes, Aisha. After this, what did we calculate?
Electric potential due to dipole.
Dipole, right? So electric potential due to dipole. So we had a dipole, like minus Q and plus Q, and the distance was 2a. And then in the middle, we calculated at the point which is making an angle theta.
Sir, you'll send this notes?
Yeah. So I will send you the. So I will send it to the Learnivio team, and then they will send it. Okay. Yeah. So we calculated the potential, and we found out that this was how much, Aisha?
AP cos theta by r square.
Absolutely right. Yeah. So Kp cos theta by r square, and we found out that at axial point, so at axial point, and then at equatorial point. So at equatorial point, this was 0, and at axial point, this was Kp by r. So this we did, and then after this, we calculated the electric potential due to hollow sphere, or this is hollow conducting sphere, or hollow non-conducting sphere, or solid conducting sphere. So for all these three cases, the charges reside at the surface of the sphere. For all these three cases, so the charges are at the surface. So we had three regions, right? So we had three regions. So this was inside, this was surface, and this was outside. So what was V inside? Let's say this is R. So what was V inside, Aisha?
KQ by capital
Yeah, KQ by capital R. And what was V surface?
KQ by capital
KQ by capital R. And what was V outside?
KQ by small r.
KQ by, let's say, some distance, small r. So this was small. So this we did. And after that, what we did? So after that, we calculated the potential difference of a line charge distribution. So this was we proved that this was VA minus VP, and this was what, lambda by 4 pi epsilon naught minus, and then this was something like 2 ln V minus ln A. This was the case, right? If I remember it correctly, ln V. This was point. We are bringing a charge from B to point A, right? This was point B, and this is point A. So we are bringing the charge from here to here, and this was ln B minus ln A, right? This was let's say this was yeah. Yeah, in the case of the line charge distribution, there is no potential. So the potential was, or potential is undefined. So can you check, Aisha, what was this value? Because I have to derive this. I don't remember. You please check whether this is correct. Oh, this was R something like. Maybe this is wrong. Yeah. So the potential is undefined for line charge distribution, right? And yeah, and we have only potential difference in case of line charge distribution. Is this correct, Aisha? Is this value correct? Yes, Aisha.
I think yes, I cannot recall.
KQ by what? Okay, let me check it. That what was this? So this was. Hmm, okay, so this was. Yeah, this was minus lambda by 2 pi epsilon naught, and then minus 2 by log b minus log. This was yeah, db minus minus 2 pi epsilon. Okay, so this is ln A minus ln B, and this is minus 2 epsilon. So this was, we can also derive this like this. So electric field is lambda by 2 pi epsilon naught R, right? And we can calculate VB minus VA from, let's say, A to B minus E dr. Okay. So in this way, we know the value of electric field and we can derive. So you will get this value, right? But remember, if we are, in this case, we are taking the charge from B to A. And in this case, we are taking the charge from A to B. So this was the electric potential for the line charge. And then lastly, we learned about the electric potential due to ring charge. So we have this ring, right? And then we calculated the electric potential due to ring at this point. Let's say this is X. So this was, and this is A. So the potential was KQ by root of X squared plus A squared. So this was the potential for the charge at this point. Right, this much we have done so far. Okay. And now the next topic that I'm going to do is, yeah, so the next topic is electric field, as the gradient of potential. Yeah. So, Fia, you know differentiation, right? You are familiar with this differentiation, right? Yeah. Oh, yeah. Okay. So the electric field. Okay, so the electric field for the case of with respect to this potential, it is defined as minus of dV by d, right. So this is, whenever we take the differentiation with respect to distance, so this is called the gradient. Gradient. So d by dr is called gradient. D by dx or d by dr is called gradient. So gradient, and this V is potential. So gradient of potential, right? And then this minus sign signifies that the electric field, direction of electric field is from high potential to low potential, right? So let's say that I have a potential which is 10 volt in here, and I have a potential which is 5 volt in here. So electric field will be in this direction, from higher to lower voltage, right? This is what we mean by this negative sign. So this you have already learned in your CBSE class. So we can write electric field as minus of dV by dt. Okay, but electric field is a, yeah. Okay, yeah. Yes, I will give some time to note it down. But so, yeah, this is how we represent the electric. but you know that electric field is a vector quantity, right? So this is representing only the magnitude. Okay, we can write the electric field as vector quantity. So if let's say it has three components, electric field is in three dimensions. So we can write electric field as x component, which is in x direction, then y component, which is in y direction, and then z component in z direction. So this is how we calculate the electric. So again, this Ex would be how much? This Ex would be minus of dV by dx. So we are taking the differentiation with respect to x, right? Similarly, Ey would be how much? So this would be minus of dV by dy, and then Ez would be how much? So this would be minus dV by dz. Okay, so these will be the value of the electric field in all the direction, x, y, and z direction. And then how can we calculate the magnitude of this? So magnitude of E would be simply root of Ex square, the x component, Ey square, the y component, and then Ez square. So this would be the electric field, magnitude of electric field, right? Now, just remember that this is, so this is not the notation for the complete differentiation, right? So differentiation, we denote it like this. This is how we denote the differentiation, right? So this is called the complete or full differentiation. But we are writing the differentiation like this. So this is delta, right? And this is called the partial differentiation. So what is this is a full differentiation, or what we say complete differentiation. And then this is the partial differentiation. So what is the difference between the full differentiation and partial differentiation, right? So in partial differentiation, what we do is that, let's say that if I have, let's say V, which is 3x square y square, right? And let me write it as z square. Okay. So if I take the partial differentiation with respect to x only, right? So only if it is the partial differentiation, x is the variable. In case of partial differentiation, okay, in case of partial differentiation, only x would be the variable. If I am taking the differentiation with respect to x, so only x would be variable, then y and z are constants for this x variable. So this would be d by dx of 3x square y square z square. So 3y square z square are the constant. So I can take it outside. So this would be 3y square z square and d by dx of x square. So this I can only do it for the case of the partial differentiation. I cannot do it for the complete differentiation. If I calculate x square, y square, z square, right? So then I'll have to use the product rule. All these three are variable. Then I'll have to use the product. So this would be d by dx dx square by dx and y square z square plus by dx of y square and plus d by dx of z component and the other one. So we will have these three quantities. But for the case of partial differentiation, only x is variable. Y, z are constant. Is this clear to you guys?
Yes, sir.
Yes, yeah, is this clear to you?
Yes, but how the questions will be asked, sir?
Yeah, so I will coming to that, right? So yeah, I'm coming to that part. So the yeah, so let's say that potential is given like this. So this is how they ask the question. First, let us do the simple question. So the potential around a region is given as v equal to 3x square plus 2x plus 5. So this is how potential is given. Calculate the electric field at 3 comma 0 comma 0. So this is one kind of question. So this is the simpler question. Okay, we know that v is given. So v is 3x square plus 2x plus 5, right? So we can calculate the electric field whenever some form of potential is given. So we can calculate the electric field. So electric field would be minus of dv by dx because only x function is there, right? Y and so there will be only x dx. Ey and Ez would be 0. Okay. So you guys tell me that what is the value of d by dx of 3x square plus 2x plus 5. Quickly calculate and tell me the answer. Yes, quickly calculate and tell me the answer. Yes, what did you guys get? Any answer, guys? Aisha and Sia, any answer? Yes. So 6x, oh, how to calculate? Yeah. So 6x minus 2. Check your sign, Aisha. Check your sign. Yeah, Fia, you know that, you know about the differentiation. So these are three terms. So we will do the separate differentiation. So this is 3x square, right, plus d by dx of 2x and then d by dx of 5. Yeah, Aisha, your answer is correct, but there is a, yeah, there is a,
But it is minus d by
yeah,
dx. So the
yes,
answer will change, right?
yeah. So both the quantities will be in minus, right? Both the terms will be. Yeah.
Okay.
So, yeah, then this 3 is constant, so you can take it outside. So you take the differentiation of x square. And then for the case of this, so 2 is constant, you take it outside and then take it. And this is the differentiation of constant. So, Fia, you tell me what is the differentiation of the algebraic expression? How much is this?
Sir, xn minus 1 divided by.
Yeah, so this is nxn minus, right?
Yes, sir.
And differentiation of a constant term is how much?
It's 1, sir.
Okay, so let's say that differentiation is calculating the change, right? Differentiation is about calculating the change with respect to other quantity. So you are calculating the change with respect to x. So your x is changing and you are calculating the change in 5, a constant term. So will 5 change when you change x? Yeah,
No, sir.
right. So change would be 0, right? So change would be 0, which means that differentiation of constant term is okay. So
Okay, sir.
this
Yes.
is yeah, this is the root of differentiation. And now when you apply this xn by nx n minus 1 in this, so how much you will get? You will get 3, and this is 2x 2 minus 1, and dx by dx is 1. So this is 2. So how much you will get? So you will get 6x plus 2. So you will get minus 6x minus 2. So this is your electric field in x direction. And your y is 0, right? And your z is 0. How it is 0? Because dy would be minus dv by dy. But v is not function of y, so this would be 0. Again, ez, this is minus d by dz. Again, this is not function of z, so this would be 0.
So,
Right.
v will be not a function of y and z always.
Yeah, because for the case of y, all the rest are constant. So x is constant, so whole quantity is a constant. If we calculate the change in constant terms, so that would be 0. So this is why this is 0. Similar case for the z1. Understood? Yeah, is that clear?
Yes, sir.
So then your electric field, right? This would be how much? This would be ex I plus ey j and then ez. So ex is minus 6x minus 2 I hat and then 0 and then 0. Right. So this is your E. And we want to calculate the electric field at what? This was one question was electric field at 300. So 300. So x is 3, y is 0, and z is so electric field at 3 comma 0 comma 0. This would be minus 6 into 3 minus 2 and I. So this would be minus 18 minus 2 I hat, which means minus 20 I. So electric field at 3 comma 0 comma 0 is in the direction of x, right? And the magnitude is minus 20. Okay. So this is in the direction of minus, right? Because this is minus to minus. Is that clear to you? Guys, is this clear?
But problems will be this for.
Yeah, so the problem will be like this. I will also do some complicated question also. So in here, the function was only x. So we can have other functions also. So I will do that question after. So you guys please note it down, and then we will do the next question. Please note it down. And whenever you guys want me to scroll down the screen, please tell me. And if you have any questions, so please ask. Aisha has been around for so many months, right? So she knows that we don't hesitate to ask any question. So Fia, if you have any doubt, you can ask. Okay.
Yes, sir.
And please tell me whenever I should scroll down the screen. So please tell me. Yes, should I scroll down the screen, please?
Yes, sir.
Then put it down. Whenever you have completed a please tell me.
Done, sir.
Then, Fia, what about you? Okay, so you are taking screenshot. Yeah, so the next kind of question would be like, so you guys do this question and tell me the answer. So if the potential of a region is varying by, let's say B is x, y square plus 3x z, and let's say plus let's say 3 z. Okay, so this is the potential, right? Let me take one simple and then so let me take this xy plus 3x z. This simple one. And then find the electric field at let's say 2, 3. Also find the magnitude of electric field at this point. So this is the question. You guys calculate and tell me what is electric. Please calculate and tell. Whenever you get any answer, please tell me. Yes. Any answers? Any answer, guys? Aisha and Pia, got any answer? Calculate
Good.
it. Calculate and check.
Sir, I just got, I didn't get the answer. I don't know how to do after that, sir.
Okay, so, and Aisha, what did you get? To calculate the electric field, we need X component, Y component, and Z component. Right. So, Aisha, what did you get?
I got the X, I think.
Yeah. So, what? 6 I cap?
No, sir, I got 2y plus 3z.
I plus 3J. 2 minus. Okay, so let us calculate and check what is the answer. So B is 2xy plus 3x, right? So let us calculate Ex first. So Ex would be minus of dV by dx, right? So this would be how much? This would be minus of d by dx of 2xy plus 3x. So remember, all the others are constant, only x is the variable. So minus of d by dx of 2xy and minus of d by dx of 3x. So 2y is taken outside and dx by dx. And again similar, minus 3xz is z is taken outside, and I have dx by dx. So this is 1, and I have x equal to minus 2y and minus. Oh, you said 2y plus 3z. Okay, but sine. So this is x. Okay, yeah, and then I have also, yeah, and then I have also the y component. So y component would be minus dv by dy. So this would be minus of d by dy of 2xy plus 3x, right? So I can write this as minus d by dy of xy minus d by dy of 3x. So you see that this term
Answer will
doesn't
get,
contain.
sir.
Yes.
We'll get same answer.
What is the what?
No, sir, we'll get the same answer minus 2y minus 3z.
Yeah. So let's see what we will get. So this is the only the x component, right? But for the case of y part, you see that this is a constant term. There is no y in here. So this is 0. Okay. And then this would be what? So minus 2x is outside, and I have dy by dy. So this is minus 2x. So ey is minus 2x. Clear? Now let us calculate the final component, which is z component. Z component would be minus dv by dt. So this would be minus d by dz of 2xy plus 3x. So this would be the z component. So again, this would be minus
First
dxy.
component will get cancelled, sir.
Yeah, absolutely correct. So first component is z. So first component is 0, right? Because it is a constant. And then this is minus 3x dz by dz. So this is dz is minus. So these are the x. So this is x, this is y, and this is z. Now we have calculated all the three components. So we can calculate what is the electron. So this is ex was what? So exi plus ey, zj, and then z. So ex is minus 2y minus 3z, minus 2y minus 3z, I hat, and then minus 2x j hat, and then minus 3x what? K hat. So this is the electric. Minus 2y minus 3z I minus 2x j and minus 3x k. But they want us to calculate the electric field at 2, 3, 4. Right. So x is 2, y is 3, z is 4. So E at 3, 4. This would be how much? So minus of 2 into 3 and minus of 3 into 4, and then this is I, and minus of 2 into 2 j, and minus 3 into 2 k. This would be how much? Minus 6 minus 12 I minus 4j and minus 16. So this is minus 18I and minus 4j and then minus 16. So this is my electric field at 3. Now what would be the magnitude? So the magnitude would be simply root of 18 square plus 4 square plus 6 square. So 18 square is, I guess, how much? 18 square is how much? 16 is 2, so this is 324, I guess. Yeah, so this is 324 plus 16 plus 36. So this is yeah, 8, and this is root of 378. So this is the magnitude of the electron. Any doubt in this question? So this was a complicated question. It had all the three components. In the previous case, there were only one component, x component. But for this case, we have the electric field in x direction, in y direction, and in z direction. Any doubt in this question, guys?
No, sir.
No, sir.
Okay, so please note down this one.
So like this big questions only they'll ask, sir.
Yeah. So they can ask this kind. So we have to do it very fast, right? So
Mm.
I will give a question for your practice, and then you guys calculate. And so I will give a question as your homework. So you guys try that question and yeah, send the answer. Yes. So yes. Oh yeah. I will send the. And whenever you guys have noted it down, so please tell me so that I can slow down. Okay. So Aisha, did you note it down?
Yes, sir.
Yeah. So then please down. Whenever you guys have completed please tell me. Yeah, wait a moment. Yeah, so wait for Aisha.
No, sir.
Yeah. Noted, guys.
Yes.
Okay. So the next topic is this is completed, and the next topic is potential. In this part, we'll talk about potential energy due to different kind of distribution. Yeah, and you guys already know that what is the potential. So it arises due to the interaction of charges with the external electric field, right? And this is due to the conservative electric. Okay, and this is defined like work done in making the system. So whatever you bring two charges together, right? And then whatever work is done to make that system, right? So then there is some energy stored in the form of potential energy, right? So this is what you call potential. Whenever work is done to make anything, when you make a system, when you bring two charges together, right? Then there is some energy which is stored in the form of potential. This you have already done in your CBSE parts. I'm not talking about in detail. So I will just write that what is the potential energy of two charges, right? So we have two charges, and there is some separation between them. So let's say this is one, and this charge is Q1, and then this charge is Q2. So potential energy, right, which is the work done in making this system. This would be K Q1 Q2 by. So potential energy of two interacting charges, right? So this is potential energy due to one charge. Now, let's say we have multiple charges. So potential energy due to multiple charges. This is defined like 1 by 2, and then this is I equal to 1 to n, and then j equal to 1 to n, and I not equal to j. And this is k qi qj divided by ri. Okay. So when you have n charges, then what is the potential energy? So we can let me give you the example of three charges. Okay. So let's say you have three charges are placed at let's say some equilibrium time, not a equilibrium time, but let's say this is Q1, this is Q2, this is Q3, right? And let's say this is R12, this is R23, and this is R1. So we have to count how many possible interactions can we have, right? So how many charges we can take two at a time, right? So we have three charges and we have to select two charges at a time. So first let us pick this charge. So this will interact with this one, right? So then potential would be how much? This would be K Q1 Q2 by R1. This is the first interaction. Now this charge is also interacting with this one, right? So then we have the another interaction Q1 Q3 and then divided by R. Now what is the remaining interaction that we have? So we have this interaction, right? So then this would be K Q2 Q3 by R2. So can we have any other interaction? Can we have any other possibility? Yes.
No, sir.
Yeah. So this is the possible interaction that I can. Okay. Right. So for n charges, let's say that for 3 charges, I have 1, 2, 3. And let me also show you the example of 4 charges. For 4 charges, how many interactions? So let's say I have, and you have also done this problem in your CBSE class, but let me just revise this for you. So we have Q2, Q3, Q4, this is R1, 2, this is R2, 3, this is R, let's say 3, 4, this is R, what, 1. Okay. And we have, yeah, so I will talk about that. So we have this one. So first, let us choose this charge. Okay. So this can interact with this one. This can interact with this one, and then this can interact with this. So I have, for this one, I have 3 possibilities. Right. So let us write the potential energy. This would be how much? This would be K Q1 Q2 by R1 plus K Q1 Q3 by R13. So I am writing this as R13 distance. And then the next one is K Q1 by Q1 Q4 by R1. So this is for Q1. And for Q2, so this is Q2. This one we have already counted, right? So we will not count it 2 times. So we will count this one. This is the first interaction, right? And then this one. So 2 from here. Okay. So this is first. Let me write it. The other two. So this is K Q2 Q3 by R23 and plus K Q2 Q4 divided by, let's say, R. So this is for this Q2 one. Now let us choose this one. Next one, which is this one, Q3. So this I have counted, right? And this I have counted, so remaining is this one. Only this one is remaining, right? So this would be how much? This would be K Q3 Q4 divided by R2. So uh, I have how many? So I have, for this one I have 3, and for this one I have 2, and this one is 1. So how many interaction do I have? How many total interactions do I have?
6.
6, right? So 3 plus 2 plus 1. So I have 6 interactions. 6 interaction for 4 charges. Okay, so for 4 charges, I have 6 interactions. And generally, if I have n charges, so if I have 4 n charges, number of interactions, this would be n into n minus 1 by 2, where n is number of charges. Okay, so you can check for 3 how much this would be. So let us check. For 3 we have calculated, right? For 3 this would be 3 and 3 minus 1 by 2. So 3 into 2 by 2, which is 3. So we are correct. For 4, we have calculated 6. So this is 4 and 4 minus 1 divided by 2. So 4 into 3 divided by 2. So this is 6. Right. So we can calculate for 5, 6, 7, 8, 9, whatever number of charges we have. Is this part clear to you? Yeah, is this part clear? Yes, guys, is this part clear?
Yes, sir.
Okay, so please note down this part. This you have already done in your CPSC class, but for the revision purpose, just note it down. And then we will do some question based on. Whenever you guys want me to scroll down the screen, guys.
Done, sir.
Done. Okay, Fia, noted. Oh, you are taking the screenshots.
So I already have this student score.
Yeah, what are you saying?
So I already have this, so you can scout.
You have already noted this down.
Yes, sir, in the CBSE class.
Okay, yeah. Then note down this one. Note down. Okay.
Done, sir.
Okay, Fia, noted. Okay, so now let us do one process, right? And before we do that, we also know that the work done, right? So work done in bringing, let's say, some charge from initial to final power point is also change in potential energy, right? This we know from work energy, right? So just recalling this, let us do this one. So we have three charges are placed at the vertices. So three charges of magnitude q are placed at the vertices of an equilateral triangle of side A. Okay. So first question is find potential energy of the distribution. This is the first question. Second question is that if, okay, so first let us and then yeah, so we have three charges.
Sir, can you scroll up?
Yeah. I will give the time to put it down.
Okay, sir.
Uh, we have so this is an equilateral triangle, right? This is Q charge, this is Q charge. So first question is very simple, right? This is A, this is A, this is A. So we have to calculate the potential energy of this distribution. So you guys calculate and tell me what is the potential. Yes, you guys calculate and tell me what is the any difficulty. Yes. What did you guys get? What did you guys get? Aisha and Pia, what did you guys get? Yeah, KQ square by E. So we have, remember, we have three charges, right? Not one charge. So let's pick this charge. So this will interact with this one and this one. So this one would be KQQ by A, and then this one would be KQQ by A. So these two we have calculated, and then remaining one, this one. So this would be again KQQ by A. So this is how much? This is KQ square by A. This is KQ square by A, and then this is KQ square by A. So this is 3KQ square by A. This is the potential of this distribution, right?
Okay.
Okay, please note it down. Please note down the question, and then we'll do the second part next. Please. Whenever you guys have completed, please tell me.